Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced de Moivre's theorem, which showed us how to raise complex numbers to integer powers and find a neat way of calculating them without kind of using a binomial expansion formula and instead just writing them in polar form and taking that power into the argument of the complex number. And in this video what I want to do is I want to look at some of the properties of complex numbers. Specifically we're going to look at the complex numbers that lie on the unit circle in the complex plane and see if we can derive another, or at least motivate, another way of writing the complex numbers known as the exponential form, and in turn derive something called Eulers Formula, which is a very famous formula, and as well Euler's identity. So I'm going to go to the tablet and we're going to title this Euler's Formula because that's what we're going to try and arrive at, which is going to be a way of writing complex numbers using the exponential function. And I said that I want to start off by talking about the complex numbers that lie on the unit circle in the complex plane. That is the set of complex numbers that lie on a circle of radius 1 centered around the origin. So those complex numbers are going to be parameterized by a function of the form. So we would have a function of something like we'll call f of theta equals cosine theta plus I sine theta. So all those complex numbers that lie on this unit circle are given by this function here f of theta. You can describe those complex numbers by this function f of theta. And for some value of theta, that will map you to that particular complex number that you want to look at on the unit circle. So notice here that f of theta, or f, is a function from the real numbers to the complex plane, or to the complex numbers. And we can see that here because theta is simply just a real number that I can put in. And when I put in that real number, it takes me to a complex number because I have a real part here and an imaginary part here, right? So I've got this complex number that maps out. And because it's simply just a real function, it's a function that only depends on a real variable, I can use my usual calculus on real numbers, which you've learned about in the other part of the course, and also in A level. In other words, I can differentiate this function with respect to theta. So, what is df by d theta? df by d theta in this situation is going to be minus sine of theta plus I cosine of theta. Now, realizing that we can factor out I of this expression, we realize we can write this as I times cosine theta plus I sine theta, where we're using the fundamental property that I squared is minus 1. In other words, we've got that this is I times f of theta. F as a function of theta here, right? We assume that f is a function of theta as we did above. So that is, we've got that the derivative of f is simply just a constant, now it's a complex constant, times my f itself. Okay, that's an interesting property. What's another property that we've got? Well, we know how to multiply complex numbers. So we also have f of theta plus phi is f of theta times f of phi. Right, we know that just from the multiplication of complex numbers on the complex plane. And if we look at these two properties, namely the derivative of f just gives a constant times f, and that f of theta plus phi is equal to the product of f of theta and f of phi, that looks a lot like the exponential function, right? So recall the exponential function that you've seen in A level that's normally written as e to the x satisfies d by dx of e to the x is equal to e to the x. In other words, the derivative of the exponential function is the exponential function. And it also satisfies e to the x plus y is equal to e to the x times e to the y. So that looks a lot like this function f of theta. So maybe we start to think, well, maybe we can write f of theta as something like e to the x or e to the theta. But notice there's kind of a major difference. When I differentiated this one, I got a factor of I down, but when I differentiate our exponential function, I just get back the exponential function. I don't get any sort of constant in front. But more importantly, I also realize that e to the x is a function from the reals to the reals. In other words, from R to R. and f of theta is one that maps to the complex plane. So is there a way that I can extend the definition of the exponential function so I can put in real numbers and that maps me to complex numbers? Well, this is an important point now to kind of discuss what we mean by the exponential function. Now, there's going to be a lot more kind of discussion in the notes about this, and you can think about the exponential function in terms of how it relates to exponential growth, of kind of growth, say, of how much money is in your bank account each year. And that's normally kind of how it's shown in A-level, and also that's kind of how it's been shown historically. But I want to kind of specifically focus on a more calculus point, which is that the derivative of the function equals itself and this property here, which I'm going to write as kind of something a bit simpler, which is just to say that that e to the power of 0 equals 1. But firstly, I think it's important to note here a kind of important remark. So it's important to realize that e to the power of x does not mean e times e times e going on x many times. It simply just does not mean that. That doesn't make sense. Right? It doesn't even make sense when you put in negative integers. And you know that e to the power of minus 1, you have a definition of this. You say that it's 1 over e. But you can't say that's e times by itself minus 1 many times. So there's just no hope of kind of thinking of it in this way. Not for real numbers and not for negative integers, not for 0 and not rational numbers either. But what you can realize it as is for natural numbers, right? So if I can put in natural numbers, if I put in something like e to the power of 3, that indeed does mean this number e that's related to exponential growth times e, in other words, e multiplied by itself 3 times. So it only means this thing here when we take a natural number, when x is a natural number. So as I said, I want to kind of think about this function, not in terms of derived kind of from exponential growth, but in terms of its derivative properties. So suppose that I'm trying to find a function. So suppose that I have a function f of x that satisfies df by dx equals the original function and f of 0 equals 1. So I just want those two conditions. Is there a unique function that emerges out of these two conditions? In fact, it turns out there is. In fact, what we're actually doing here is effectively solving a first-order differential equation, which you'll look at in more detail in the calculus component in the second semester. And in particular, this is actually something called an initial condition, and given any first-order differential equation with an initial condition, it must have a unique solution. But let's see if we can think about how we can derive f here, what we think of f. Well, the obvious thing is you would say, oh, well, this is e to the x. E to the x satisfies this, and it also satisfies this. But can I build it by thinking about power series? So you've hopefully you kind of talked about power series in the calculus component. So this arrives at a definition. So let's kind of start a kind of new page down here, and let's put a definition in. Let's define the exponential function not as this idea of exponential growth, but from this derivative property as the following. We'll define it as, we can write it as e to the x, but it's also traditionally written as exp of x, is this infinite series from n equal 0 to infinity of x to the n over n factorial. And it turns out that, so this is what is known as a power series, and you can prove, at least using the calculus parts of the course, that this thing has what is known as an infinite radius of convergence. That is to say that if I put in a value of x in the reals here, that this series necessarily converges. And it turns out the value that it converges to is exactly the same as the one that it would converge to if you built it in this exponential growth way. That requires a proof, but we won't go into that here, but you can prove it yourself using the calculus techniques that you've learned. So what we see here is that we can think of the number e, for example, is simply the value that what this series converges to when I put x equals 1 in. So that's how I can think of the number e in this setting. And we see that this indeed satisfies that derivative property. Why does this seem like a reasonable thing? How would I construct this? How would I dream this up necessarily? Well, I realize just because I know how to differentiate x to the power of n, right? And if I take an infinite sum of x to the power of n's, then I can kind of construct it in such a way that when I differentiate those things, that it equals the original thing. And that's how kind of how I've constructed this. I've constructed this by really thinking about these properties here, that the derivative must equal itself and that f of 0 must equal 1. Well, I can clearly see that this thing does satisfy that when I put in 0, it equals 1. And I can check just rather simply, right, that d by dx of x is simply going to be the sum from n equals 1 to infinity of x to the n minus 1 over n minus 1 all factorial, right? And that follows because when I differentiate x to the n, I bring down this factor of n, which is going to cancel with one of these n's from my n factorial. So that's just going to leave an n minus 1 factorial on the bottom. And I decrease the power because I've differentiated it. And why am I starting at 1 here? Because the first value was the number 1, and then when I differentiate a constant, that's equal to 0. And I can just redefine this sum now, right? I can just shift it along, redefine it as, like, say, from k equals 0 to infinity of x to the power of k over k factorial, which is exactly just x of x. So I've kind of constructed this series as something that when I differentiate it, it gives back my initial series, right? That's how I've kind of constructed it. I've dreamt this thing up by just really thinking about properties of derivatives of x to the power of m. And then all I need to show is that thing has an infinite radius of convergence, and that's what I define to be this function, the exponential function. It's the function that when I differentiate it, it gets back itself up here, and when I put in f of 0, it equals 1. Fantastic. Okay, so it seems reasonable that we can define it in that way. And what we notice is by defining it in that way now, there's no restriction necessarily to putting in x as a real number here, right? I could put in x as a complex number. So that is, I could have x of ix, or e to the ix. Well, what would that equal? That's the sum from n equals 0 to infinity of ix all to the power of n over n factorial. And this thing makes sense, right? We don't know yet that it converges, right? Because it will require some more complicated mathematics to do that, because we'll be talking about convergence in the complex plane, and you've only talked about convergence in the real numbers so far, not in the complex numbers. But what you can take to be true here is that that indeed does converge. So for every value of x I put in here, that does converge to a complex number. So this thing just gives a complex number. We don't know what that complex number is yet. And this series makes sense, right, in the sense that all it's doing is just multiplying complex numbers and adding them, and we know how to do that. It's just doing that infinitely many times. And indeed, I claim that this thing converges. Okay, so now we can look at this thing. We've got this new function, this e to the ix. It's defined in this way. It's defined as this infinite series that we say is convergent, and it satisfies all the properties that we wanted before that we had of f of theta. That is d by dx of e to, let's go back to theta just to write it in that notation. So we've just changed the name of the variable here from x to theta, is I e to the I theta. So that's looking a lot like this function f of theta. And similarly, you could just use the Cauchy product to prove that e to the I theta plus phi is equal to e to the I theta times e to the I phi. If you just use the Cauchy product of the series, you can prove that rather simply. Okay, so it seems that this thing, this e to the I theta, satisfies the exact same conditions as f of theta, and f of theta was cosine theta plus I sine theta. So it seems to imply here that e to the I theta is cosine theta plus I sine theta. So that kind of arrives at our kind of theorem that we're going to state, which is otherwise Euler's formula, which says let z equal, or let z be in C such that Z is equal to cosine theta plus I sine theta, then Z is equal to e to the I theta. In other words, e to the I theta is equal to cosine theta plus I sine theta. So we can write any complex number on the unit circle as an exponential function, as this exponential function that we defined up here. So this is another way of writing complex numbers in this e to the I theta way. And we can extend that, right? It's fairly simple that if I can write any complex number on the unit circle in this way, I can write any complex number on any circle of radius r by just multiplying by r in front. So that means I can write any complex number z in the complex plane by just simply taking e to the I theta and multiplying it by r, where r is simply the modulus of that complex number. So that effectively is just kind of stretching my circle so it covers the whole complex plane. So let's just kind of finish off by looking at some examples of how we can write a complex number in this exponential form. And it's fairly simple that we can say some examples. And as usual, I'll just cover one example here, and you can look at more of them in the notes. So the one that I'm going to look at is I'm going to say, let's take z equals, say, -1 minus root 3i. We can draw that in our complex plane. So let's kind of doodle our complex plane in the corner. This thing here is the imaginary axis. This here is the real. Now it's -1 units along here and root 3 along units here. So in other words, it's somewhere around here. This is -1 minus root 3i. I can describe it by this line. And if you think about the height of this triangle, the height of this triangle is root 3 and its width is 1. In other words, that is saying that this angle here is pi over 3. So if I take what the argument of this complex number is here, I can say that the argument of z is going to equal minus pi over 2, because that's this angle here, and because I'm going clockwise, it's negative, plus the pi over 3. Which is given by minus. I can write this as, that is 2 pi over 4 plus, pi over 6, 3 pi over 6 plus 2 pi over 6, which is 5 pi over 6. Sorry, I've just realised now that's wrong. I apologise. This here should be pi over 6. This angle here is in fact pi over 6, not pi over 3. Okay, apologies for that. Okay, so writing that out now, we get that this is minus 3 pi over 6 plus pi over 6, which is minus 4 pi over 6, which is minus 2 pi over 3. So that's our argument for our complex number. And we just need to find its modulus now. So what is the modulus of z? That is simply the square root of 1 plus 3, which is 2. In other words, the length of this thing up here is 2. So we've got we know what the modulus is and we know what the argument is. So hence, z can be written as 2e to the minus 2 pi I over 3, right? Because we write it as the modulus times by the exponential form. In other words, this is kind of making it that we're on a circle of radius 2 centered around the origin, and then this means that I move 2 pi over 3 radians clockwise away from the real axis, which gets me to exactly this point in the complex plane. So that's where we're going to conclude. And in the next video, what we're going to do is we're going to look at how to kind of solve polynomial equations that are now polynomials that are complex polynomials. So before you've looked at real polynomials, that is kind of polynomials with real coefficients. Let's now look at complex polynomials, in other words, complex equations or polynomials with complex coefficients. So, as always, I recommend that you read the notes, which have some kind of additional explanations in here, especially about how to derive this exponential function from exponential growth ideas, and then as well attempt any problems in the module handbook relating to what was covered in this video. So thanks very much for watching, and I'll see you in the next one.